Next up, we have Professor Kei Okada from the University of Tokyo, who will talk to us about whole body control for JSK humanoid robots. Professor Okada has been involved in MoveIt and ROS for a long time. In the olden days, he actually hosted Dave Coleman, I believe. He was still a grad student. So it's a long shared history in MoveIt. So very happy that he's here and presenting his research.
Okay, can you hear me? Okay. So thank you for introductions. And I'm also a peer-to maintainer here. And so today I talk about our work at JSK about humanoid robots. And unfortunately, we are not using MoveIt so much for humanoid research. And today I'd like to discuss about why that happens here. So this is a slide that I always use to introduce our laboratories. In JSK Laboratory, there are about 50 members in our lab, and we are doing the research on building and utilizing the robot. So in work on building the robot, as you can see this video here, we are developing the complex robots that have a body structure similar to that of the humans. And we are studying the intelligence that grows and adapts like human here. And in the research of using the robot, we are studying the robot systems that support our daily lives in everyday environment using the robotics platform like PR2 or HRP2 or other robots. And the key feature of our laboratories are system integrations and real-world applications. And as you can see in this video, we have a lot of robots, and all of which are modeled in Useris. That is a programming language that we have been using more than 30 years. And this is one of the Lisp dialect. And run on common integrated software, and here, including recognition, control, reasoning, and visualization, and so on. We are trying to run all robots in the same robotic software systems. And the key feature of our laboratory is that all students conducted experiments with the real robots with the goal of realizing the tasks that are similar to or beneficial to the humans in the real world. But unfortunately, motion planner is not positioned in the core of these integrated systems. But it doesn't mean that we are not interested in the motion planning research. So instead, we have a long tradition of collaborating with excellent motion planner researchers. So from 1999 to 2001, James Kaffner here worked with us as a postdoc with his RAVE program and conducting the world first research on motion planning with the humanoid robots. So from 2010 to 12, Ross and Liankov developed the integration of the OpenRAVE and ROS in our laboratories. And of course, in 2014, Dave Coleman here worked us with the MoveIt and connected with his MoveIt software with our humanoid recognition and motion generation systems. But even so, motion planning system is not included in our integrated system as presented in the previous slide. So today's presentation, I'd like to discuss that reasons. And the first thing to consider is that in real-world robotics applications, the real-time loop of perception and motion is very important. And there is no time to spend on planning the motions if it takes a long time. So here we have exoskeletal type human robot controller. So this is a human in perception motion loop. And this is a typical autonomous perception motion loop that robot carries boxes while observing its position and orientation of the boxes. So in particular, humanoids are mainly dynamic motions and algorithms that takes long computation time. And also if that algorithm computational time change every time are very difficult to use. And only exception in our laboratory is this fetch robot here, which was a movie running the lower layer of the motion controller and avoid collisions with the body and while the robot moves the arms. However, if we can assume there are no collisions like these situations, as shown in this video, we skip the motion planning layer and send our program trajectory directly to the robot. So another reason is that planning the joint position trajectory alone are not enough. So for example, in this video, robot is trying to lift the heavy object here, and we need to take into account not only the limit of the joints of the robot, but its balance and force that robot can apply, and also the torque that robot can generate. So in order to generate motion such as a large number of the constraints, we usually use optimization method in these researches. And if torque limit not taken into account in these equations, you can see in this video, while robot is trying to lift the heavy object, the torque exceeds the limit of its motors, and robot falling down like this because of the safety limit of the motor driver is activated and causing the robot to drop out of the power. And another direction of our research recently is multi-contact motion generation and control. And instead of the robot standing at the same position and move its bodies, we are interested in the move whole body while contacting multiple points. For example, in this video, the robot climbs the stairs or steps with its hand and feet, and even using the knees in sometimes. So in this study, the task is viewed as a transition between the multiple contact status, and the following two problems are addressed. The first one here is how to choose the contact posture to take in the series of the sequence. And the other is to plan the trajectory between the selected contact postures. And in this research, we use the running method for both problems. So in here, the system runs the evaluation value of the next best contact posture according to the environment and robot status. And this trajectory planning, this student uses the MPNet motion planning network to generate the collision-free trajectory in order to find the trajectory in the shortest calculation times. And note that these colored circles, which can see in this video, that represent the torque of this robot. And as we discussed earlier, the control system needs to monitor the circle, torque, so that it does not exceed the specified value to, the torque limit of the motor driver to avoid the burnout of the motor of the robot. And in addition, contact is not just about objects attaching to each other, but also our interest or our tasks contact need to deal with a force and times. For example, video in the left, robot is wiping box or writing some figures, or here robot is scooping the ball. And it's important to determine how long and which direction the force is applied to the object or a box or balls. And also, a video on the right here, the timing between robot and object is very important for tennis playing, ball hitting tasks, or using a shovel to pick the ground. And it's necessary to change the distribution of the force throughout the body depending on the location and the timing of the contact in order to keep the whole body balance. And also, our target object is very complex. So instead of solid bodies used in the classical motion planning example, the object that our robot is using is flexible, and these are very difficult to model in computer. So for example, the task of cutting vegetable to make the curry rice, it's necessary to handle the event that the object split after each actions. And here, we are also working on grasping the deformable object like papers. And in this video, the robot is scrubbing dirt over the plate. And if we want to solve this kind of motions or tasks in the motion planning framework, there is a problem of not only the generating the arm trajectories, but also we have to consider how to model this kind of complicated state changes of the environment and the objects. And the complexity is not only the object and the environment, but also the body of our robot is very complex. And or I can say that it's a flexible and difficult to model. So here is a structure of our tendon-driven robot. And this is a URDF model of the robot, but it's only a rough representation. And tendon-driven robot use 2 wires to control their joints like humans, and they are not equipped with the sensors to measure the angle of the joint like traditional robot manipulators to emulate the human bodies. And so that we need this kind of the learning or network system to estimate the joint angle from the length and the tension of the wires. And furthermore, the robot body is constantly changing like a human. For example, trajectory of the wires are changing while the robot is moving. And also frictions of the joint may change over the time, making it difficult to model in the URDF models. So here, we use a learning method to acquire the body model, which we call the body image. And in this video, the system observes the relationship between the angle of the joint and the length and tension of the bodies, wires, while the robot is moving the hand randomly, moving the arms randomly. And as it learns the relationship of these 2 parameters, it reduces the error between the ground truth of the joint angle and the estimated joint angle values from the wire length and tension of the robot. So by using these round models, robot can control its arms to desired positions. And even if robot grabs a heavy object, the error is not changing so much because of we have a round model using not only the length of the wire, but also the tension of the wire too. And in the last part, in this video, we intentionally cut off the power of some motors. And there is some anomaly detection system that can detect the such situations like this. So this is another interesting project that we are interested in recently, because as we see in the movie to introductions, integrating navigation and manipulation planning has been the wish list for the many years. And in the future, I think we need to consider flying robot, integration of the flying robot and navigations and manipulations as well. So this video above is showing the flying robot that can transform with multiple links. And we use a motion planning technique to find the movement path from one space to another space. But if we want to manipulate object with this flying robot, in this case, we want to carry this box. We need to solve the multi-contact problem like humanoid robot. And we need not only change the postures, but we also have to control the force of the joint or the thrust of the propeller so that flying robot can carry or grab the object not to fall. And we also show some example of the humanoid robot. With thrusters that human robot can walk and fly in the sky. So currently, robot is just executing the pre-programmed program here. But if we want to do motion planning, we need to handle two modes, like walking planning and also flying planning. So this is a last slide. So current challenges in our laboratories is limitation-aware motion generations and multi-contact motion generations. And also, we need to deal with a complex object like a deformable or flexible in manipulations. And also, we are dealing with dynamically changing bodies. So it's very hard to model in the static representations. And the example presented today are specific to individual robots and tasks. And this technique is not integrated in the common software that can be used in all robots in our laboratories. So I think we need the good or general framework to incorporate them. And I think the motion planning framework is one of the potential candidates. And in order to run such a complex, in order to run in complex or arbitrary environment, we need to use motion planner all the times because the tasks which I showed today is very specific to the specific or determined or prepared environment. So we want to run motion planning all the time in our systems. And in order to do that, I think the motion planning needs to be stable and real time. And also understanding the limitation of the lower layer control or hardware. And hybrid control, which I run today, could be a good candidate for this direction. So I think in addition to that, I think the motion planning to handle a lot of limitations, not only the trajectory or orientation, the positions, but also the force and timing and so on. Also, if we look at the real-world applications in our laboratories experiment, I think most of the tasks relating to the contact while the robot is moving. So in classical meaning, motion planning is a technique to generate motion trajectory to avoid collisions. But most of the videos that I presented today, robot is trying, the motion of the robot is the way to when and how to contact environment and object. So I think this is very important direction for the, I can say, next motion planning techniques. So that's all for today, and thank you for listening.
Thank you very much for this, really fascinating presentation. I think there's definitely a lot of work to be done in contact bridge manipulation, research-wise, but also in terms of actually getting this supported in a generic way in software. And I think, a lot of the things that you pointed out are definitely things to think about. Do you feel like your own software has provides a good solution for this, that this is something that we should look at to adopting and incorporating into MoveIt?
Yeah, I think our software, the software presented today is very specific to the task or robot. So for us, we always trying to, how can I say, how to generalize each examples. And so I think that we need to, how can I say, extend or expand our solution to more generic frameworks. And motion planning, or I can say that state search technique could be a good example, because optimization is also the state search technique in local optimization, local states. So
so there's a couple things I think that are kind of weak spots, right? That is sort of the contact richness, the task constraints, that makes it hard. But it's also this dealing with how to incorporate control. Like we're doing this decouple planning and MoveIt, where we do geometric planning followed by generating the forces and torques. Is that do you feel like that's a fundamental limitation that is somehow making it hard to do the kind of things that you want to do?
Yeah, so I think general, how can I say, framework is there is a high-level reasoning and motion planning and control. But in my point of view, motion planning should be put in the lowest layers, because that is, how can I say, last resort for not break the robot or generate the, how can I say, not to generate unwanted motions like hitting the robot hit himself or robot hit humans or environment. So in order to do that, I think motion planning need to, how can I say, model the controller hardware inside of the systems. So currently, motion planner only models the robot description or geometric representation of the robot, but it also models the controller inside of the systems. Then we can, how can I say, we can use a motion planner in very low layers. I mean, that means that we can use motion planner all the time for all the robots in our laboratories. So this is, how can I say, idea or view, but I don't know how to realize that in real implementations.
Yes, Michael.
So you basically stole away my question from me, Mark. But nonetheless, Kei, first, thank you a lot for this awesome presentation, especially in your time zone.
Yeah.
Second, if I'm correctly informed, happy birthday.
Oh, yeah, thank you.
And then lastly, basically following up on Mark's question, because it's one of my lines of research a bit. I do think there is a lot of merit in doing geometric planning and then only characterizing different phases of a motion, for example, being executed by different controllers or different control profiles. And what you just described sounded to me like you basically want the full physics simulation, including the full simulation of the controller online at a, I don't know, 50 hertz rate, which is asking for an oracle, basically. But the one thing you can definitely do is to say, in order to chop through a cucumber, you do need to do a motion such that the blade cut through the cucumber. And then the controller you need in order to cut through this needs to change from the transit motion controller to a controller that can chop through something. Do you think there's merit in that, or is that also a dead end?
Yeah, I think it has a great advantage, because if you think about a problem on task and motion planning, a task planner try to understand how motion planner works to generate the sequence of actions. So if we consider the same things between the motion planning and controller, motion planner need to understand how the controller works. So I think, of course, there is a lot of merit to separate or create some interface between the different levels, like motion planning, control, high-level reasoning. But I think there have some limitation in future. People want to integrate, or how can I say, interact with different layers or different tasks, different, how can I say, functions of the robots. So the problem is how we can create such interaction between different modules. And I think a lot of people working on the task and motion planning, but I think all the direction is most of the people are trying to put everything in one modules. And the same thing would be happen to motion planning and control.
Okay, I have just one comment. I apologize for failing you on using Move It with humanoids. Long line of people who've tried. I made some pull requests, but I never got them merged in. They were difficult to get merged in to Move It to support humanoids.
I know.
Good to see you. Happy birthday.
Yeah, thank you very much for having me.
Yeah. Okay. Yeah, thanks so much. I think we should probably move on to the next part of our schedule. Yeah, thanks again, Kei, for your presentation. Hope you can stick around if you're not busy celebrating your birthday. I think in the happy hour, people would like to talk to you and discuss more of all the issues that you brought up. But yeah, if you need to go, I completely understand. It's probably very, very late for you now.
Yeah.